Go. Okay, so we're recording now. So what we have been working on so far has been systems of equations. I'm trying to, oh, it's not turned on. Is systems of equations, right? Which is more than one equation, and we're trying to find their common solutions, right? And that's the stuff we've been working on. And our first time we did it, we were using graphing, right, to show that the solutions, the common solutions, were those points where the lines that we were graphing intersected, right? And then we started doing them algebraically, and we used all sorts. Ooh, I don't know what's going on there. We used all sorts of means for doing that. But what we learned is that we could have one solution, right? Which was when those graphs crossed, right? And that intersecting point was our one solution. We learned that we could also have infinite solutions, infinite solutions. So, and what was that? When we had infinite solutions, what we had were lines were like multiples of each other. And so the graphs of the lines sat right on top of each other. Pretend that those were right on top of each other. And what that looked like algebraically was, say one of my equations was like x plus y equals 2, and one was 2x plus 2y equals 4. Notice that this line right here, well, this second line right here is the same as this line, just multiplied by 2. And they would graph right on top of each other. So everything that is a solution, every point that is a solution for x, y would be the same in both of those, because notice every point that they would land on in that graph would be identical, right? Especially if I drew the lines correctly and they sat right on top of each other like that. The other type of solution set would be no solution, right? And no solution happens when the lines are parallel. They are never going to intersect, right? There will never, ever be a common point between them, and in which case we have no solution. Now, I am talking to you about these because I want you to think about them and I want you to remember them, because there might be a potential extra credit question on the test regarding them. So I want you to keep that in mind. And remember, I'm recording all this. It's going to be on PowerSchool. You can go back and look at it if you need to. But I will probably maybe be devising an extra credit question that deals with the types of solutions that you can have dealing with systems of equations. And we only have 3 types. We can have one solution, infinite solutions, or no solution at all, right? And we found all different ways of doing this, and we used graphing to find the solutions, which I already told you will not be on that quiz test. The other thing we used was substitution, and I didn't do a substitution example the last time I saw you guys, so I'm going to do a quick substitution reminder. For those of you who were able to get the extra credit question, you only got the extra credit question if you came to class. That will be the same today with today's assignment. Today's assignment will be 3 questions. One is an extra credit question, and the only people who receive it will be you guys who came to class, that opportunity for the extra credit points, right? So when we have substitution, say we have 3x minus y equals -4, and we have x plus 3y equals -28. The only time we're ever going to want to use substitution is when we have something like this or like this, which is a variable with no coefficient in front of it, meaning we're talking about one of them, right? Otherwise, you're going to be dealing with fractions, and it's so much harder to use substitution. You might as well use elimination if we're getting into things like that. With substitution, what we want to do is solve for one of the variables and then plug it in for the other. So I'm going to take this bottom equation and I'm going to go y of x plus 3y equals negative 28. And I'm just going to solve the whole thing for x. I'm going to get x all by itself. And when I do that, all I have to really do is subtract 3y from both sides. And I get this equation, which is x equals minus 3y minus 28. And the important thing to know about that is when x equals something, that means anywhere I find an x within the system, I can just plug in minus 3y minus 28. And the reason that that is useful is that then I can eliminate. I've eliminated one of the variables. I can solve it for y and then go find out what x is. So since I used this bottom equation right here to solve for, I'm going to plug in to the top one. So I have 3x, right? 3x minus y, but I know that x equals minus 3y minus 28. So I'm just going to plug it in where the x was. And then I also have my minus y equals negative 4. Minus y equals negative 4. And now I don't have any x components, so I can figure out what y equals. And then we can plug it back in here to figure out what x is. I don't know why I made that little mark. I didn't even think my pen touched. So we're just going to solve right now. We're going to distribute this 3, and I'm going to get minus 9y minus 28 times 3 would be 75 plus 9, 84. Minus y equals negative 4. I'm going to combine my like terms. I have minus 9y minus y. That gives me minus 10y minus 84 equals negative 4. And now we're just going to start undoing everything that's done to this y, and we're going to figure out a numerical solution for y. And the first thing I'm going to do is I'm going to add 84 to both sides because we're doing an inverse of PEMDAS, right? We're doing the opposite of PEMDAS, so we're going to do our addition and subtraction first. So I'm going to add 84, and I get negative 10y equals 80. And I still have this negative 10 being multiplied to y, so I'm going to go ahead and I'm going to divide by negative 10 and divide by negative 10, and I get y equals negative 8. And the cool thing is once I know what my y is, it's really easy to figure out what my x is going to be. Now, I can go all the way up to the original equation, or I can come right here and go x equals minus 3y, but what do we know y to be? Negative 8 minus 28. No matter which equation I use, I should get the same answer. Sometimes it's better to go to the original equation because who knows, maybe I screwed up somewhere along the way here, but I know that I didn't. So minus 3 times minus 8 is positive 24 minus 28, which gives me negative 4. And so I know that x equals negative 4 and y equals negative 8. And that is how substitution works, right? We solve for one of the variables, we plug it in, we find a numerical solution for the other, and then go plug that in and figure out what the other variable is. And the other thing we did, yeah? Yeah. I combined my like terms. I had a minus 9y minus y. So that's like saying minus 9 minus 1 gives me minus 10. So I just combine these like terms. I put these two terms together. And then so I wound up with minus 10y minus 84. Does that make sense? Yes. I subtracted each, yeah. Yeah, kind of. I solved it for x, right? I'm trying to get x all by itself up here, right? I took this from this equation, and I'm trying to get x all by itself, so I'm undoing everything being done to it. So here I subtracted 3y, but I have to do it from both sides or I change the equality. And so when I do that, these cancel, right? 3y minus 3y is just 0, but it doesn't cancel over here. I can't combine them. So I'm left here with x, right, equals minus 3y minus 28, because I can't combine these two. I just have to put them together like this, right? And so when I did that, I then took this problem up here, right? And we solved this for x. So this is 3x minus y, right? I moved that. I'm using this problem right here, right? So 3 times x, well, what do we know x is? It's minus 3 minus 28, so I just plugged it in. Because we know that x equals minus 3y minus 28, so where the x is right there, I just plugged in minus 3y minus 28 minus y, and then I go and solve the whole thing for y. Does that make sense? Okay. Play with them a little bit, and if you have any more questions with that, I'm happy to answer them. So that was a substitution question, but we also did elimination, right? And I'm doing an elimination example, but I'm doing a pretty easy one because we're going to go ahead and do another one with the 3 variables. So I wanted to make this one pretty quick. And so I had, what did I have? I had 2x minus 3y equals negative 1. And I had 2x plus 3y equals negative 19. And you might look at these and think they're pretty similar. Maybe they're going to have a common answer, like maybe they'd be infinite or maybe they would be no solution, but they are neither of those things. Because of these negative signs in the middle, it really changes things up for us. So we're talking about elimination. So we're trying to create an opposite. So we either need 2x in opposite signs or 3y in opposite signs, but these are already in opposite signs, right? I have a minus 3y and a plus 3y. So if I were to just add these two together, they're going to eliminate the y all by themselves. So I don't need to manipulate these equations. And I chose this one because it is simple, because we are going to have to manipulate the ones with the 3 variables. So if I didn't have opposites, I'd have to create opposites, but because I already have them, I can just go ahead and add these two together. So if 2x plus 2x equals 4x, minus 3y plus 3y is just 0, which is what we want. Minus 1 minus 19 gives me minus 20. And so I can easily find out what x is in this one, right? Right now I have 4x, but all I have to do is divide by 4, right? Because that's the opposite of multiplication. And I get x equals negative 5. And I already know what my x value is. So I can take either one of these equations. I'll take the top one because the numbers are smaller. So I'll take 2x minus 3y equals minus 1. What I already know is that x equals negative 5. So I can just plug that in. 2 times negative 5 minus 3y equals negative 1. So now I just have to do the math and I'll know what y equals. 2 times negative 5 is negative 10 minus 3y equals negative 1. And now we're doing the same thing. We're just taking everything off of the y. So I have a negative 10, so I'm just going to add 10 to both sides, which gives me negative 3y equals 9. Now I still have that negative 3 being multiplied to y, so I'm going to do the opposite of multiplication, and I'm going to divide out negative 3. And I get y equals negative 3. And those are my only two variables, so I know my solution is negative 5, negative 3. Always list our x value first, right? Alphabetical order. Now, I can check this. I can know if I'm right because I can just plug both of these numbers in for x and y in either equation, and it should be true, right? It would have to be true for both of them for it to be a solution. And I'm not going to do that because it's super time consuming, and I really want to get to a 3-variable one, which takes a while to solve a 3-variable problem. And so we are going to do an example 3-variable, and then I'm going to show you guys your assignment, and I will let you go, hopefully early, right? So we've got 3-variable example, and our 3 variables are going to be x, y, and z, right? And this is nothing new. We've been doing this, right? We did it last week or the week before, the last time I saw you. So here we have 6x plus y minus z equals negative 2. And here I have x plus 6y plus 3z equals 23. And then I have minus x plus y minus z equals 5. And so if you remember correctly, when we did these problems, what we did is we broke them up into 2 sets of equations. So I am going to go use this as my A equations, and I'm going to use these two as my B equations, right? I can choose any of these that I chose from the first one. I'm choosing these two because I can already see that my X is going to be really easy to get rid of here. So I've got my A's, which are 6x plus y minus z equals negative 2. I always put a line in my z so you could tell the difference between that and my 2's because they look fairly similar. 6y plus 3z equals 23. Right, that's my first set. And then I've got my b's over here, which are x plus 6y plus 3z equals 23. Those of you who used Photoshop, I don't know if any of you guys did use Photoshop, but Photoshop's got a 0. It's super obvious when you use Photoshop on these problems because they are computer-generated solutions, and they use a very specific notation that I'm sure people weren't understanding. And I just automatically gave them zeros for it. And that will be true too when we do the quiz. If you use Photomath, not Photoshop, but Photomath, you'll get zeros for those. So let's look at what we have to do here. We need to create an opposite. I know I want to eliminate x on this one because they're already opposites. If I just add these two equations together, my x is going to disappear. So since I know I want to get rid of x here, I want to get rid of x here as well. And so I have a 6x. So I want to know what I have to multiply this equation by to get myself a negative 6x, right? So I'm going to look at this and go, what do I multiply this x by so that it's negative 6x, so that I'm creating an opposite? And so none of you seem to be shouting out the answer, but I think you know the answer to that is negative 6. So I'm going to multiply this whole equation by negative 6. Down here, I'm going to just start by putting in the top equation, right? Equals negative 2. But here I need to distribute. So I have minus 6 times x gives me negative 6x. So when I add these two together, my x's are going to disappear. Here I have minus 6 times 6y, which is going to give me negative 36y. And then I'm going to have negative 6 times 3z, which gives me negative 18. Wow, that just doesn't want to write there. Negative 18z. And here I have 23 times 6, and I don't know what that is, times negative 6. I just know it's going to be negative something, right? 6 times 3 is 18. Carry the 1. 6 times 2 is 12. 138. So I have negative 138. And when I add these two problems together, these disappear and I no longer have an x value. Y minus 36y becomes negative 35. Y negative z minus 18z becomes minus 19z equals negative 140. Now, here when I look at this problem, I don't have to do anything to eliminate the x, right? When I add these together, they automatically eliminate because x minus x is just 0. 6y plus y gives me 7y. 3z minus z gives me plus 2z. And then 23 plus 5 is just 28. And so now if you notice what I have with my A and B, because I chose to eliminate x from both of them, is I have a 2-variable equation, right, with the same 2 variables. This one has a yz, this one has a yz, which means that I can put them together, which was the whole reason for doing it. So I can take this one and I can go minus 35y minus 19z equals negative 140. And then I can take this one and I can put it down here as 7y plus 2z equals 28. And so now I'm going to solve these for y and z. And then once we find that, we can plug the yz back into one of the equations, and we will have our 3 variables solved, right? And I know that this is labor extensive. This is the hardest thing we've done all semester, which is why I'm taking extra time with it. So I need to look at this right now and I go, what can I eliminate? And I can go, okay, well, I know that 7 goes into 35. 2 doesn't go into 19. So for that, to get rid of z's, I'd have to find a least common multiple. It's a pain. But I know that 7 goes into 35 because 7 times 5 is 35. And so what I'm going to do is I'm going to multiply this whole bottom line times 5, right? Because that will give me a plus 35y, and here I have a negative 35y, and that's what I want is opposites. So I'm going to start by rewriting the top line, negative 35y minus 19z equals negative 140. And now I'm going to distribute this, and I'm going to get 35y, right? Now we have an opposite, so when we add them together, they'll drop, plus 10z, right? And check this out. This happens to equal positive 140. Convenient for us. So here's what happens when I add these together. Negative 35y plus 35y is just 0. So those go away. Here I have minus 9z plus 10z, which gives me negative 9z equals 0, right? Negative 140 plus 140. And then what I get here is going to just be z equals 0, right? Because I divide that by negative 9. Once I know that z equals 0, I can plug it into either one of these two equations. I'm going to go with my 7y plus 2z. What is z? Z is just 0, so plus 2 times 0 equals 28, right? 2 times 0 is 0, so I'm left with 7y equals 28. When I divide that by 7, I get y equals 4. So what do I have? I have z and I have y. The only thing I'm missing is x. And so I can take any of my original equations and I can plug it in there and I can solve for x. So if I have, let's go with minus x plus y minus z equals 5. I'm using that one. It's right up there. What do I know? I know that z equals 0 and y equals 4. So I have minus x plus y. Well, that's plus 4 minus z. So that's minus 0 equals 5. Right? So I have minus x plus 4 equals 5. And then I can subtract out that 4. And I get minus x equals positive 1. Right? But what happens when I divide this by negative 1? Because I don't care what negative x equals. I care what x equals. So I'm just going to divide everything by negative 1. And I get x equals negative 1. So my solution is negative 1, 4, and 0. I know that this is labor extensive, but sometimes that's how math goes, right? I can always check and see if I'm right because I can plug these three numbers in for x, y, z into any of these three original equations, and they better all be true. That shows that they would be a common solution. Does anyone have any questions regarding any of that? We lost Emily, which means she's going to lose her opportunity at the extra credit component. I'm going to stop recording since nobody's asking